Amazing. Okay. Well, hello everyone. I'm happy that so many people are interested in knowledge distillation. And yeah, so this talk is going to be focused on a work that I've done some time ago now. I think at least 1 year ago, trying to understand a bit the mechanisms behind knowledge distillation. And in particular, I ended up doing some empirical investigations that could, and you're gonna be the ones that tell me at the end if they actually do, shed some light on the inner workings of knowledge distillation. So before going into knowledge distillation, just one or two words about me. I've already been presented, and I'm very happy to actually have been asked to present this work. I'm from Rome, and I live in Switzerland since now 6 years, and I'm currently a PhD in computer science at ETH. In particular, there's this ETH AI Center where I am most of my time. And my thesis is focusing on continual learning, but in particular, the, let's say, perspective on continual learning that is theoretical foundations of it for deep learning models. So how do we efficiently learn online with deep learning models so that we basically do not forget what we've learned before, right? So the optimization side of it. But while working on continual learning, I found actually some interesting evidence regarding knowledge distillation. There are some works in continual learning that use knowledge distillation, and they were effectively they were able to use less data. So in continual learning, there's one of the main approaches they use is replay buffers, let's say, to avoid forgetting the previous data, and it works very well. And there are some approaches to use knowledge distillation with replay buffers, and I noticed in the results that they could achieve much better performance with smaller buffers. And the only thing that they actually changed was the objectives. So the fact that they were using the outputs of the trained model instead of the labels. So this is what brought me to knowledge distillation, what brought this project to life. Now I leave the bibliography directly at the beginning of the slides. So in case you're gonna see in the slide some references. I'm gonna be using the letters that you see here in front of the paper. Usually I'm going to put the letters in brackets so you know that I'm referring to one of these papers. Basically, there's a lot of papers on knowledge distillations nowadays, and before going into all the different forms and ways in which knowledge distillation is used today, let me first introduce it properly. So a bit of notation. I'm going to be talking about input and labels, even though knowledge distillation is applied to a wide range of applications today. We denote by X the input and Y the labels. Then I'm going to be talking about network logits, so the outputs of a network function F that is parameterized by theta, and K is going to be the dimension of the logits, so the dimension of the outputs. We denote this by Z. And typically, if we want to, for instance, represent distribution over these labels, then we transform this network logits with a softmax, and the softmax formula is here on the right. Yeah, actually, I just realized that on the top, this ZI on the numerator should be a ZK for the consistency, but basically the softmax takes the input vector in the k-space gives us a vector in the k-simplex, and the temperature scales the softmax in a way that you can see in this figure below the formula. Basically, higher temperatures will make the probability distribution more and more uniform, and lower temperatures, so closer to zero, will make the distribution closer and closer to a one hot encoding, kind of like the labels. So the softmax interpolates between the max and the completely uniform distribution with the temperature. And this is how I denote the final network prediction. So after taking the network output and passing it through the softmax, we call it P f of tau. Maybe I found a way to show you my cursor. Okay. No. Okay, doesn't matter. Yeah, and also one thing that I'm gonna use, especially later, is that the network function can be decomposed usually typically in a linear head, so just one linear layer, and then this phi mapping, which is called backbone, or I'm gonna call it features afterwards. Okay, after all the notation, we can say what it's a typical knowledge distillation, or the simplest, not typical, nowadays not typical, but the simplest knowledge distillation objective looks like. And I'm gonna be focusing, at least in the work that I'm talking about, we focus on the simple objective, the simple formulation of the objective, because simpler is better for understanding. We try to remove as many layers and confounders as possible to study in a targeted manner the effects of a specific change, right? So if we start from the label training objective, we usually have, in the cross entropy, for instance, objective, we're minimizing the KL divergence between this one hot encoding of the labels and the output of the network in the once passed through the softmax, so in the probability simplex. But in the knowledge distillation objective, we do the same, but we change the target distribution from the one hot encoding to be this distribution from the teacher. We call a model teacher simply because it provides target. It usually is a trained model. It usually is a model that is much bigger and that performs very well. But actually, as we will see, there's all sorts of types of teachers that have been used in practice, and in the more theoretical works, also randomly initialized teachers have been used, for instance. So the teacher is the model that provides the target, and we will call the student the model that instead learns from this teacher targets. Actually, in this work, we will talk about student pair, because we will always be comparing two students, meaning that there are two equivalent networks that are learning from two different targets. One is the teacher provided target, and one is going to be the labels target. So the original, let's say, label training objective. Okay, so now there's two facts that are important and that I think made knowledge distillation as famous as it is today. The first one is that knowledge distillation allows to compress. So if we take, and this is what was shown in the original works, the proposed knowledge distillation now 10 years or more than 10 years ago, if we take a very, very big model, we may maintain its performance and compress its size by 10 or even 100 folds just using knowledge distillation. So just changing the target distribution as I've shown you before. And this, of course, is incredibly useful. But the second fact that was noticed maybe a bit after the first proposal of knowledge distillation is that we can get a student network that is equal in size to the teacher network to perform even better than the teacher network, even though it's just learning from the teacher outputs. So we have this improvements in generalization that come from distillation for free, let's say, by just self-distilling, as the technical term is, the network into itself. So these two facts basically brought to the explosion of knowledge distillation in today's literature. So in deep networks used today, knowledge distillation is actually ubiquitous. We can find it in vision, in language, in audio, to learn cross-modality, learn graph neural networks, specifically the relations between the nodes, also general and transformer architecture to learn the attention maps. And the data, initially, it was the same data as the teacher, but actually the data can be also synthetic data, or it can be some new transfer data set, basically. And now regarding the formulation of knowledge distillation, the original formulation is the one that I showed you before, which is basically called response-based today because it's on the response of the model. So the responses of the teacher and the students are kind of pushed to be similar, but there's other forms of knowledge distillation that have emerged since, like feature-based distillation, so pushing the student model features, so intermediate hidden layer representations, to be similar to the teachers, or relation-based, so pushing the teacher and the student to, in a contrastive way, kind of to see the same differences or similarities between pairs of data points. And all of these different forms of distillation are used in so many applications and so many learning tasks. So we already mentioned model compression, but of course also quantization, neural architecture search, continual learning, as I said at the beginning, which is where I first got into distillation. Ensemble learning, so learning from different teachers, federated, and I'm not gonna finish reading the list because it's many of them. And in this figure here, I'm showing basically some results from this mini LLM paper that shows, it's actually showing a new distillation-based technique for model compression, but you can see also the kind of naive sequential knowledge distillation that basically compresses as well the teacher architecture, which is, you can see the size above, like this first one is 1.5 billion parameters, and the teacher performance is almost reached even by the naive distillation already with half of those parameters, basically. So it's especially relevant today in the era of very big models that require very big compute to be trained, right? If there's a big model sitting around, for sure it's a good idea to just distill it in a smaller model and use that smaller model for deployment, for instance, because the inference cost and the energy use is going to be much lower. Okay, but taking a step back, given that distillation is so used, how much do we know or understand of distillation? And there's mainly two hypotheses that have been kind of thrown around in the literature and explored a bit. And these two hypotheses are the ones that I'm gonna talk about today, and the ones that are explored in the paper. And there's a recent survey that I left in the bibliography that explores related, let's say, accounts of distillation. And it's surprising to me that, even recently with the surge of use of knowledge distillation, we still don't have a good theory for it that once and for all kind of establishes why knowledge distillation works. So you can see it even in this recent survey, these two hypotheses are still maybe the main kind of concepts that we have to talk about knowledge distillations today. And so the first one is labels moving. So it says that basically the benefits that we see in distillation come from a type of regularization that is due to the softening. So this moving that comes from the soft labels of the output distribution. Labels moving in itself is a technique that has been used in deep learning before knowledge distillation even, to actually improve generalization. So it makes sense that one would suggest that knowledge distillation itself is acting on the deep network as a regularization coming from the soft label, so the smoothed distribution, compared to the, of course, labels that are one hot targets, right? And the second hypothesis is called dark knowledge. And the idea is that the regularization, if you want, from knowledge distillation, which gives a good bias, so efficiency in learning to the student model, comes instead from an implicit relation structure that is implicit in the teacher output. And it basically determines which classes are similar to which other classes. So basically what the dark knowledge hypothesis says is that compared to the one hot targets that have just the information about the true label to be predicted, the knowledge distillation targets have additional information. So there's not only the max in the distribution, there's also some weight, some mass on the other labels, and the exact way in which this mass is distributed is basically what determines the interclass similarity that comes from the teacher. Now, what do we do in this work? There is one important dimension in the study of knowledge distillation that has mostly been ignored. And in this work, we focus on this dimension to try and study theoretically the mechanisms of knowledge distillation. And this is the dataset size. So we, instead of focusing on a fixed dataset size, which is what is typically done in the papers that maybe argue for labels moving or for dark knowledge in understanding knowledge distillation, we look at what happens in knowledge distillation compared to label training as we vary the dataset size. So basically, we systematically try to evaluate this existing knowledge distillation theories by varying one, let's say, one variable, by varying one fundamental aspect of the previous reported empirical evidence that had not been varied before. And we try to see if anything new emerges. And basically what I'm going to try to argue in the rest of the presentation is that there is an empirical bias in the knowledge distillation literature, which has brought to believing that some theoretical explanations would be enough to account for knowledge distillation, but that these same explanations break down when you actually vary this factor, the dataset size. And also I want to insert some of my own speculations on the mechanisms that underlie distillation that come from my observations in all these experiments that we've done. Okay, so the first thing that I'm going to talk about is this data efficiency. So first, let's talk about the empirical, the setup of the empirical study. And I call it an intentionally simple setup because, as I was saying before, in theoretical counts of deep learning effects, we want to simplify as much as possible to target the effect of one specific factor, right? So if we were to put too many factors to vary together, we basically would risk having confounders in our conclusions and observations, and not being able to draw final conclusions actually, and answer our questions. So what do? We take two equivalent networks. These are the two students that I was mentioning before. One is going to be trained with knowledge distillation, and one is going to be trained with label training. How are the students equivalent? Well, they have the same architecture, of course, but they also have the same initialization, and they use the same hyperparameters. And as you know, hyperparameters are essential in deep learning performance. So we decide to bias a bit the comparison in favor of label training to avoid biasing it in favor of the knowledge distillation. So we take the hyperparameters that are optimal for label training, and in particular there we take the hyperparameters that basically are optimal for label training with an amount of data that is equivalent to the teacher training data. We refer to this amount of data as the kappa equals 1 scenario, because kappa is for us the fraction between the amount of training data of the students and the amount of training data of the teachers. So we train the teacher with, say, n samples, and we train the students with m samples, and then the fraction m over n is going to be kappa. So the percentage of training data that we use for the students. And what we do in the experiment is simply repeat this training of the two students. Of course, they're trained independently for multiple kappas. And we do this for multiple architectures, and here is the list: multiple architectures and multiple datasets. So, for instance, we take CIFAR10, but we take an extension of CIFAR10 in order to go also to the setting of kappa way larger than 1. So we go to the setting of kappa very, very small and kappa very, very large, and also, of course, kappa equals 1 to compare with the current observations in the literature. And to extend CIFAR10, we use basically this CIFAR10 5 million dataset that is actually available, and it was published with a previous paper that basically extends it with a generative model trained on CIFAR10. And also CIFAR100, ImageNet. So there's 3 vision datasets that all have labels. So we do standard supervised learning on them. And we use also this Languini Brooks dataset, which is screened text set of like texts that come from books, and it has been used already in previous work for autoregressive language modeling, and we use it in the same way, basically with the same setup to train GPT models, from mini to small and medium sizes. So we train relatively small networks and also bigger ones, and we train for the vision both convolutional backbones and VIT backbones, and we see across all of these setups the same trends, the same exact results, which is the following. So in this summary picture, you see 4 equivalent figures with kappa that is varied. In this case, we keep it below 1. So we look at the low data regime, and the test error or the test perplexity for the autoregressive language modeling. And in purple, you see distillation, and in green, label training. So there's exactly the 2 students, let's say, are compared across kappa, as I was explaining before, and then there's the gray line that denotes the teacher performance, basically. Yeah, so let's dive into it. Let's look at it more in detail. For sure, what should like catch your sight right away is that distillation is much faster in terms of the amount of data needed to achieve certain type, a certain amount of performance. So it's always below the label training curve. In particular, here on the CIFAR 10 benchmark, I highlighted that distillation can use up to 3 times less data to achieve the same performance as label training, which is a great saving in terms of data. And we also notice, if we look vertically instead, that for especially the lowest ranges of amount of data, distillation actually performs much better. The gains in test errors, so the gains in generalization performance are around 10%, 25, 15 for the vision benchmarks, and 10 for the test perplexity in the language benchmark. So compared to the observations in the literature that looked only at the kappa equals 1 part, and in kappa equals 1, the observations were around of 1-2% of generalization improvement. We see a much bigger effect of distillation in the low data settings. And all these results are actually averaged over 5 seeds, and you see very little standard deviation because the differences are so big, actually. So this is great. Actually, here I have to make 2 notes, and you will find the details in the archive if you're curious. So we tried assessing whether this data efficiency could translate into computational efficiency, so training the large language models, or actually not large, training our language models, the relatively small ones, with knowledge distillation, whether we could save flops. And with this naive approach, just by varying, let's say, the amount of data and comparing to the label training, actually we didn't see improvements in flops, total flops, so the computation side. And this is because the the gap between the distillation and label training also depends on the size of the teacher and the relative size of the teacher to the student. And basically, the bigger the teacher, of course, the bigger the gap, but also the higher the computational cost. So this though is a naive approach to it, because one could find ways to, for instance, distill only a few. So this, instead of randomly sampling the dataset for distillation, one could bias the sampling towards the samples that distillation, let's say, that can even make distillation quicker in reaching a certain performance level. And also one could try to optimize the number of calls to the teacher such that in total the computational cost is lower. So this is something that other papers have already tried, and actually one could effectively use distillation for improved computational efficiency. But in our, let's say, naive setup, if you just take distillation as we did here and call the teacher every time that you have to update, then it's just not going to be convenient. Okay, so now that we have this empirical setup, let's go to the theoretical part. So now we want to look at these two main theories that I mentioned before, and we want to try to see if when we vary the data percentage, if we can still confirm the intuitions of these theories, or if instead we can effectively reject them. The first one that we look at is labels moving. So as I was saying before, labels moving is relatively common technique in deep learning to improve generalization, and simply taking the one-hot label encoding and mixing it with a uniform distribution. This UK symbolizes a uniform distribution on the output. And this basically results in more or less what you can see here in figure 3, which comes from one of the papers on labels moving as an hypothesis for knowledge distillation. And so you can see that instead of having a 0 probability on the classes that are not the correct class, there is a non-zero probability, but it's uniform. So this means that there's really no extra similarity structure. So there's no dark knowledge hidden in these outputs. Just to be more exact, what I mean by the similarity structure is that when you look at two different samples, or better, the outputs of two different classes, maybe averaged over all the inputs for those classes, you see that it's not only the class corresponding output dimension that has some mass, but there's also mass on other classes that are somewhat similar, considered similar to that class. So they have some probability of being also correct according to the model, but it's not uniform. So for instance, in cipher 10, there may be some probability given on the airplane class, given that the correct class is truck, but maybe there's no probability on animal class, right? Because the two are considered very different. And this similarity structure is not present when you apply labels moving. But some observations led people to believe that even when you have 0 similarity information between categories from the teacher model, knowledge distillation can still improve the student models, as this is citing from this paper. And so what they propose is to have a teacher-free knowledge distillation. So you don't have a teacher, you basically just have the correct class let's say, one hot encoder plus this labels moving. And what you see in the results here is that, well, for instance, CIFAR 100 tiny ImageNet in our report in this table, if we look at CIFAR 100, which is what I highlighted here because we did the same experiments also on CIFAR 100, slightly different actually because they use a teacher that is the ResNet 50 and we're going to use a ResNet 18. So we're going to have the same architecture between student and teacher. But what you see here, for instance, for this case of the ResNet 18 is that the baseline accuracy is 75.87, and then when they use normal knowledge distillation, they get a boost in, this is test accuracy, they get a boost of 1.32. As I was saying before, the observed boost in knowledge distillation usually in literature were about 1%, 2%, very far from the 25% that we can see when kappa is much lower. So 1.32, and when they report the results with this teacher-free knowledge distillation, then they have 1.49. So they claim, given that this is repeated in different data sets and different models, that the two are behaving in this exact same way. But now what do? We basically repeat this experiment, and we do it for CIFAR 100 and CIFAR 10, 5 million, for different levels of kappa, for different amounts of kappa. And we produce a similar table, but the conclusions are very different. So basically what you see here is that I highlighted again in pink the setting that is equivalent to the setting reported in this paper here. So kappa equals 1 is exactly the slice of the curve that they're looking at. But when we extend the observations to the entire curve, so we look at kappa that is less than 1, very small, 0, 0.2, 0.1, so on, we see a much different picture. And we see that labels moving, this LS column here, is not able to match the performance improvements of knowledge distillation. And especially the plus 25% the knowledge distillation achieves in the case of kappa 0.1 is very far from the more or less steady, almost constant improvements that labels moving can give at different kappa values. And this is both for CIFAR 100 and CIFAR 10. Yes, so basically the conclusion here is that distillation is data efficient, but labels moving doesn't exhibit any data efficiency. And with this simple, let's say, evidence, we conclude that we can reject this hypothesis that knowledge distillation is similar or equivalent to labels moving regularization. Okay, so given this, what about the dark knowledge hypothesis? So this is a big quote from the original Hinton paper that is basically explaining to you the intuition that I was trying to explain before regarding this similarity structure implicit in the network output. So Hinton originally mentioned that in the incorrect answers, so the probability mass given to the non-correct label output, there is information regarding the relation structure that the network learns between the different inputs. And this is one version of this theory. There's other refinements that came out with time, and one of this is the multi-view hypothesis, which is that basically a student network, so a general network, learns a feature map that is dependent on its initialization. So if you give different initializations to different metrics, you're going to learn different feature maps. And in particular, you're going to learn to focus on different parts of the feature. And the multi-view hypothesis is that when a student is trained with a teacher target, since the teacher has learned its own view of the data distribution, so it's learned to focus on some specific things, and the student may have a completely different random initialization and random optimization process, the student will learn a different view, but since it learns the targets from the teacher, it basically learns multiple views combined, which gives it generalization benefits in the same way as ensembling and ensemble models do. So now let's say version of this hypothesis that we test in our work is the following, is that the benefits of knowledge distillation actually come from a higher feature similarity, where the feature here, as I was saying at the very beginning in the notation part, we mean the last layer representations before the head, so before the linear layer. So we want to test whether knowledge distillation comes with higher feature similarity between the student and the teacher. And how can we test this is now the question. And the first way that we try to test this is by simply a cosine similarity between the student and the teacher feature maps. So we would take the normalized inner product averaged across the data set, basically, of this feature maps. And these plots show the results that we get with this measurements. As you can see, sometimes distillation leads to higher feature alignment, maybe this cosine similarity, sometimes lower, and there's no clear trend with kappa. For instance, for language, it's increasing, for vision, it seems to be decreasing over kappa. The stars are actually the points that we sample in the different, with the different seeds. And there's also way higher standard deviations, right? So somehow the randomness here is affecting the results. Given that these results are mixed and inconclusive, we decide to go to a different measure of feature similarity, which is the feature kernel alignment. So how do we measure feature kernel alignment? Basically, we first have to define the feature kernel, which is simply the inner product that is operator that is defined by the features of the network. So any feature map defines a kernel that also defines by the representative theorem that functions that the network expresses. So basically, since the head is a linear layer, then the function of the network is a linear function on top of this feature representation, right? So it can be expressed using the kernel view instead. So yes, so the output can be expressed as a linear combination of the similarities that are given by the kernel and the labels. Given the feature kernel, we can look at the similarity between the student and the teacher kernels. But how do we look at the similarity? Well, we can basically do an inner product, or better, a cosine similarity in the kernel space. So imagine if for the whole data set, you take all the kernel values for the student and the teacher, and then you take an inner product there and you normalize it. This is basically what the center kernel alignment measure does. And the reason why we move to the kernel space is twofold. One is that this allows us to remove all the randomness that comes from permutation equivalences in network, which could come from just initialization, for instance. So it's a more robust measure than just taking directly the feature similarities, the cosine similarities. And the second is that it better represents this idea of similarity that we want to test, right? So our hypothesis, if you remember, was to test whether the teacher basically, through knowledge distillation, gives the student its own metric of similarity between different data points, right? And the kernel exactly exemplifies this. So which results do we get? Well, we see clearly in this pictures that distillation, at least in vision. Okay, let's focus on vision first, and then I'll make a note about the text case. So in vision, we see that distillation consistently induces higher feature kernel alignment. And as we vary the fraction of data used to learn the students, we clearly see with, again, very concentrated distribution. So the standard deviation is once again very small here. That compared to label training, knowledge distillation has much higher alignment with the feature in terms of feature kernel alignment. And this is strongly correlated with the performance improvements that we've seen. So in the data efficiency of distillation at the plots that I showed you before, we saw a very similar curve in terms of test error, right? So the feature kernel alignment correlates strongly with the performance improvement in distillation. And for vision, instead, we see that after a certain amount of data, this is not true anymore. And somehow, despite the fact that distillation is still outperforming label training, we do not see a higher feature kernel alignment in distillation compared to label training. And this is really an open question for us in this work. We have investigated different kinds of metrics and also different kind of distillation in language. For instance, we've tried forward distillation, so forward KL and reverse KL, and we've tried to play a bit with the objective, but we could not find a setting where language was in terms of feature kernel alignment similar to vision. So this is an open question. It seems to be that the mechanism that is behind the performance improvements in knowledge distillation in vision and language is different. And one, let's say, speculation that I can throw in there is that this depends a lot on the relative size of the output space compared to the feature space. Because, for instance, in language models, the output space, which is usually the vocabulary size, is much bigger than the representation, the feature dimensionalities. So this could lead potentially to higher difficulty in transferring the feature similarity or feature kernel information from this very high dimensional projection of it, which is the output that the student actually gets. But this is just speculation, and it's actually in an open question, in the open questions list that I have at the end. So it's still unclear why knowledge distillation could result in all this performance improvement in language, but it looks like for vision, feature learning is key to understanding why knowledge distillation works. There's also another evidence that I wanted to show. This is, I believe, from C4 100. And here, basically, what do we measure? We measure the kernel alignment between different students. So not between the student and the teacher, but just between different student models that have different initialization. And we take 3 knowledge distillation students and 3 label training students, and we repeat this for different levels of kappa. And the numbers that you see here are actually the amount of training data. So the lower one has kappa, I believe, 0.05, or maybe it's 0.2. The second one is 1%, and the third one should be 2%. Yeah. And what we see here is that the kernel alignment between the students that are independently trained, but trained from the same teacher using knowledge distillation, is much higher than the alignment of the same students with the label trained networks. And then the alignment that the label trained networks have with other label trained networks. So we see that basically the knowledge distillation students somehow form a cluster in the feature kernel space. So the space where we use as a metric the kernel alignment metric, the knowledge distillation networks are much more clustered, so much more close to each other according to this metric. And again, I'm going to throw in there speculation here. There is basically, this is evidence that knowledge distillation substantially biases the optimization process of the student network by reducing, if you want, the space in which the network is, the space of possible feature maps that the network learns. So instead of being a much bigger space, now it's the space dimensionality is reduced. And this, of course, can be tied to standard arguments in generalization theory and generalization bounds to argue that you get a better data efficiency, right? So this was one of the intuitions that I had while doing this work. Even though it's actually difficult to formalize, and I have personally found no paper that properly formalizes this intuition of a smaller effective dimensionality in the network space. But this is what I think this kind of evidence points to, is that, yeah, we see that the student models are kind of tied to a specific, if you want, group or type of set of feature maps and representations. Yeah, and I should also mention, just to add there to the speculation, that there is actually some work, theoretical work in knowledge distillation that looks at knowledge distillation in terms of the bias variance trade-off. So as some of you may know, the, let's say, final generalization error of model in classical generalization error theory can be decomposed, if it's the mean squared error, it can be decomposed in a bias and a variance term. And basically the argument of some papers, now it's more than one, and I left them in the bibliography, is that knowledge distillation effectively can reduce variance, but at the price of increased bias. So what does this mean? It means that basically, as we train with more and more data, we're probably, and this is also what we see in our observations, we're not gonna escape from the predictions that the teacher provides. So we're not going to generalize much better than the teacher, because the teacher itself is not optimal, right? So it's in expectation not providing the correct labels. So because that is because it has some errors. But we will maybe get much quicker convergence. This is all tied into the same picture, although I don't have written out theory for this. I think this is the way to go. Somehow tying feature learning into the bias variance trade-off. I thought there was maybe a question in the chat or something in the chat, but I somehow lost it. So if you have a question, maybe just unmute yourself. Or
I guess it's just that from the organizing perspective, we're already at 6, so we're already at the hour. So maybe we can then converge to the questions part.
Yeah,
recording.
Perfect. Yeah, I'm actually, that's perfect. Thank you, Lina. I lost track of time, but I'm actually done. So I have some extra things here to show if the questions go there, but otherwise just quick recap and conclusion is that what I hope you take away from this little presentation today is that we have data efficiency with knowledge distillation, somehow much faster convergence, and that theoretical accounts of knowledge distillation may exhibit empirical bias. And this is in general true of, I think, any deep learning theoretical account that is based on empirical evidence, that there may be empirical bias and vary in some factors that have not been varied in the empirical studies is one way to discover them. And in particular, what we discover with our setup is that labels moving and knowledge distillation are very distinct. And that actually feature learning seems to be the key to understanding knowledge distillation. Also, as I mentioned before, an open question is that knowledge distillation seems to behave very differently in language autoregressive modeling and classification and vision. And this is a question of why does this happen? But yeah, happy to take questions now.